Allô? Bonjour tout le monde? Allô? OK. Malheureusement, cette session va être en anglais, mais j'ai entendu qu'il y a il y a traduction quelque part, c'est vrai ou? Ouais? D'accord, ouais, d'accord. Ah ouais, juste sur l'écran, là. Okay, so good morning. My name is Chad Harkness, and I am the Chief Revenue Officer of a startup called Geminus AI. And I'm joined here with Amanda Fagnou, who I will introduce in just a second. But today we are going to be speaking about AI for mission critical assets and mission critical operations. So the way we're going to run this session is after introductions. The goals that we want you to take out of this is, first of all, we're going to orient you to the oil and gas sector, right? So the energy sector. Some of you may be from that sector, some of you may not. So we will introduce you and orient you to that. And then Amanda's going to walk through a little bit the digital and AI landscape in the industry. And then we're going to get into how specifically artificial intelligence, how it has been used and how it will be used to control mission-critical infrastructure. And then at the end, we'll also extrapolate the learnings and the takeaways to other industries. So that's going to be roughly the order of march. We're obviously going to leave lots of time for questions. And we'll get kicked right in. So I'm lucky to be joined by Amanda. Amanda is a 20-plus year executive who is now holding the job of the Director of Strategy and Marketing for Schlumberger, which is now called SLB, the digital division. So some of you may know, some of you may not know that Schlumberger SLB has an over $2 billion business in purely digital. So yes, they're known for physical assets and for large equipment, but they also have a 30-year-plus business and a very large material business that has seen all the evolutions of digital, which Amanda's going to walk us through. So Amanda, very happy to be here on stage with you.
Thank you, Chad.
And let's just kick right into it. So maybe you can give me a little bit of the context of the scale and stakes of oil and gas.
Thank you, Chad, and happy to see you again. Chad introduced SLB very well and SLB Digital. I'm just going to go through a little bit what is a mission-critical operation. And oil and gas, there's very few industries that actually rival with the complexity of oil and gas and the stakes. In this space, the spend is about $1.3 trillion dollars every year to keep oil and gas and energy for the world. And it is really very complex in a sense where the operations you see here in the slide here are offshore, so it's critical. The planning lasts many years, and the trillions that are invested are there to answer questions of what is out there under the ground. There's no visibility. We count on sensors, on data to be able to extract where to go and get the oil. Where is it? Is it economical? And once we find it, we have to drill. We have to go blind to steer a well, to land it in the sweet spot, and then to extract. And then the operations continue, and any of the especially when we talk about AI, any of the decisions that are made are irreversible. They impact billions of dollars. So getting it right in terms of digital, especially in terms of AI, is very important. Probably right in our industry is definitely wrong. So you really need to make sure that you have the guardrails and you're doing and taking the right decisions. And if that decision is taken by AI, and today some decisions are taken by AI, this needs to really be trusted. That said, in this industry of $1.3 trillion, there is a huge opportunity from digital Today, the Reichstag, there is a study that just came out in June. They estimate the value that digital and AI will be bringing to the industry over the next 4 years at about 500 billion, all dependent on the adoption of agentic AI. That sets the market for digital itself at about 50 billion a year. So it's really high stakes, high money, and how do we deploy AI in this industry will become very critical.
That's excellent. So, very material. Maybe you can give the audience just a little bit of the background of the evolution of digital and oil and gas again, just to kind of set the scene.
Yeah, I mean, this is the slide here that's shown just shows the operations that happen. What do we do in oil and gas? The first part is around planning. There's a lot of digital involved in the planning, from the seismic processing. When we take seismic data, we're talking here about petabytes of data of seismic that you need to model, simulate, and be able to decide where is the traps, where is the oil. Then you have to do a lot of interpretation, again, modeling, knowing where are you going to drill, how are you going to develop. Decisions that are made are deciding on which facility, which pipeline. These are, again, $1 billion of things, of decisions that software has enabled in the past. So we've been for decades providing solutions, software. It was in mainframes, then it moved to PCs, and the very recent evolution was cloud. So we need the elasticity. The elasticity of the cloud has been given us the power to reduce that cycle from years to months, and sometimes from months to days. And not only that, but the certainty, because you run so many models, you simulate it so much that you're able to take it to days and take a lot of scenarios, and then therefore more certainty. And a facility that costs $1 billion, you basically are sizing the facility to the right reservoir. In recent years, the cloud has been a major shift and transformation. The platforms, the hyperscalers that came in. But in the lower part that you see here is operations. And in operations, we're talking about drilling. We're talking about production, automation of maintenance, health production. Here is no longer the cloud because we're really in the operation side. So there's the edge computing, edge AI. It's been a big thing for us for a little while now. And obviously, the whole thing rests on data. And this industry has a lot of data that we can exploit and feed the AI model to be able to help the physics-based models as well for decisions. So the evolution has been a lot of players, the main players from domain like ourselves, but also hyperscalers, a lot of partnerships. And obviously, the next revolution that we are seeing right now that we're working on to build the future is agentic AI. So imagine in operations that are high risk, high complexity, how can you enable agents and take this whole operation to autonomy? And that's not a dream. Autonomy today, we are drilling well autonomously. It's decided all by AI to land the well in the sweet spot in the reservoir. We did it even before automated cars. We are doing automation in production as well, but the whole question for our industry, because of its complexity, is how do you scale it? So it goes from just point solutions, 1 well, 2 wells drilled autonomously, to all the wells drilled autonomously. So that's more or less the evolution that we've seen over the last decades in our industry. And we, as a company, have been leading that, partnering with the best in class to bring those tech and make them essential for our high complex operations.
Excellent. And then the ecosystem, maybe you can walk me through a little bit the ecosystem as you see it?
Yeah, so the main thing here for us, and we have decided to do it quite early, is nobody can do it alone, especially in the agentic era that we're entering right now. It's not about what we build. It's really about how do we partner with everyone in this in the tech space to bring the best in class to our company. Here you see just some of the partners that we have. And this is what we call it, the six layers ecosystem. We obviously work with all the cloud provider. We're cloud agnostic. Our operations span the whole world. We work in 80 plus countries. We have some sovereignty requirements. With some customers that don't want their data because the data is proprietary, is competitive. They don't want their data to be stored in the cloud, so we have it in country. And the operations, as I said, are really critical. So if one of the cloud providers goes down, our operations cannot go down. And therefore, we have to switch to another cloud provider of another region to be able to address that. So we do partner with all. The edge, as I mentioned, is very important for us to be able to automate, to make assets, vans, etc., open, close on the rig automatically, chemical injections for producing wells. That's important to have the computing power sitting in the operations. With the emergence of AI, we have a lot of partners. Here you see some of them, but NVIDIA, we've been working with NVIDIA since 2008. It's almost 20-year partnership. They have designed the GPUs back then for us that are done for the high power compute that is required for seismic data and seismic processing. And that journey has been ongoing. Today, we're working with them to create foundation models, which are, if you wish, LLMs for our industry. That we are working to design the chips that will be for the high performance of our foundation models. And of course, we have cybersecurity, a key thing. If we get hacked in one of our systems, the consequences, again, on the rig could be really catastrophic. So we do have a huge focus on cybersecurity. Trust in our industry is important. And then finally, obviously, we have data. Data is very important. I will touch on that a little bit later on. But AI with the wrong data can be really having consequences. And finally, we operate a lot with some of our players in our domain, obviously, to make sure that their equipment is automated for the operations.
Do you want to maybe just also give a little bit of a comment on the relationship between the ecosystem and the customers and, make versus buy, this kind of concept?
Yeah, so it's what we've seen in our industry, and maybe in other industries, the parallel is the same. A lot of our customers or operators want to build the solutions themselves. So they have a lot of IP that they have built over the years. And then with agentic AI specifically, we would see that to continue as well, because they have their proprietary data. And they need to customize the workflows to their data and their operations. So what we did is really what you see here is as platforms. We have two platforms, one for the workflow and one for the data and AI layer that feeds the workflows, obviously, and make sure that the workflows are using the right data, complements the physics-based models with AI models as well. And our platforms are open. This is why we have this whole ecosystem. So they're open, extensible, and we have a lot of customers that bring their IP on our platforms. No one can do it alone in this world of agentic AI. And we have partners, such as the one, Geminus as well, that we're talking here with today. And we do have a lot of even co-petition, what we call co-petition. Sometimes it's our competitors. So we don't build everything. We decide on what we build ourselves, and we decide on what we open for the ecosystem to contribute to. We do have a marketplace, actually, and add-ons, a lot of extensibility in all of our tooling to be able to accommodate this ecosystem, and our customers are themselves part of our ecosystem.
Excellent. All right. So as we start the transition and get to focus in on AI, so what, in your opinion, Amanda, will make or break AI in oil and gas?
It's a very good question. It's really the first thing, in my opinion, that makes or breaks AI is data. The data, and in our industry, the data is huge amounts of data. One well generates a petabyte of data over its lifetime. Facilities have thousands of sensors, so we get a lot of data, and it's stored everywhere, all over the place. We typically use about 10% of the data in our day-to-day life. And the way it has been handled historically is really people managing the data. So it's a lot of people cleaning and preparing the data. In the era of AI, that's not possible, because either you don't have enough data, you're using only 10%, and that's a waste, or the data can be not appropriate, and therefore the outcome is bad. So the way we're addressing that problem is by focusing on the data and AI layer, by doing a bridge, which means you don't have to lift all of your data and take it to the cloud. We all know that's super costly, and the journey of transition is huge. So we're building a bridge, which means it connects to all of the data sources and the databases. Then it uses AI to clean the data, ingest it, uses ontology models to actually complete it, QC it, and then it feeds the models, both AI and actually workflows. So that's the guardrail around the data. The second one, what we found is really, it has to have a domain AI, a domain tech stack. We are, as I mentioned, it's no longer about LLMs. LLMs are good. We use all of them, by the way. It's the choice of the operator to bring their own LLM, or they can let us bring our own LLM. I mean, we use the generic ones. But for our industry, we built proprietary foundation models. These models are trained on data from our sector, public, proprietary data that we have. And they're not one model like we're talking about now, frontier models in the trillion parameters. The foundation models we're building are in the billion parameters. So the smaller, they are very specialized. They use the LLM, they complement the LLM, obviously. And then these models are what make the guardrails. The decisions made by AI have guardrails through these models. They use the right data. Then we build on top these guardrails to make sure that decision is, especially critical decisions, that they are grounded in physics and the real world models, that they don't go off track. So a lot of the work is around that, the trust in the model. Because otherwise, the outcome is not the right outcome. And in our industry, we can't tolerate that. So these are the main thing I would say. The data, feeding the models, and then the models themselves, and then on top of that, the guardrails that make them critical, for critical decisions, make them AI make the right decision.
And how is then SLB positioning itself in that context? Like, how are you shaping up to take advantage of this opportunity?
So again, it's all around the ecosystem. So we're partnering with our customers, ourselves, and leveraging our platforms. For us, really, what we bring is to make sure that this AI doesn't live on a world on its own. So it's embedded everywhere. So around all of this stack, we have our agentic AI assistant, Tela, that would be embedded. So basically, the people don't have to go out of their applications. They sit in their applications that they use on a daily basis, and they can get the agentic AI interface that they can use within the application. And then, if they want to go beyond across applications or use other workflows, they can actually exit and be talking to the agentic assistant directly to access the AI models that we have. And our touches, as I said, is we have built this domain tech stack that makes sure that there is trust in the output, that it's not a black box. There is traceability, you know what the AI is doing, and we always have the human in the loop, what we call the human in the loop, which means that there's always someone that is making sure that the model, the training, the outcome is within the guardrails.
All right, and the last question for you then. Maybe can you give the audience a little bit of color on 3 lessons from the journey?
Yeah, it's important to say it's a journey because we've been on it. We've been always doing this, meaning every tech that's out there with our partners, we bring it to our industry, and we need to tailor it to the industry because of its complexity. And our journey in AI has been for a long time. ML has been included in our applications for a very long time. And now all of our applications have an agentic component. So it's real. We see the results as well. The learning really is, it's not about the tech, it's about the people. So if the people, the change management of the people is the big component. So first of all, the people themselves, they need to upgrade themselves to be able to understand agentic. and to be able to understand what the tooling behind is doing. I'm not talking about the people building the software. I'm talking about the people consuming the software. And the second one is the people need to trust the outcome. To be able to trust the outcome, this is when you adopt the technology. So how do we put in place mechanisms to make sure that they have still control, that you're augmenting the people at the beginning, not replacing them completely? And how do you give them the visibility on what the AI is doing? I think that's the challenge. We've seen it from other technologies before, and this one is even more important to get the people ready, the change management ready, to remove the threat that people perceive from it, and to remove the actions that can be not controlled, to make sure that the people trust the outcome. Yeah.
So, okay, now I have to ask a follow-up. So given then those concepts of trust, change management, what is the actual state of AI in the oil and gas industry from your perspective?
So we see everybody interested in it is the main thing. So everybody is now experimenting with AI. In my opinion, there's so much value that can come from it. As I've shown before, a lot of the digital and all the tooling that has been and the enablement in oil and gas has been in the planning side. The planning side is the office. You're simulating your planning. You're not seeing it in operations, right? What AI can open is really this operation part, where intelligence is going to be there, where automation and autonomy is going to be there. So I think we will adopt it. We're starting the journey. Often we tend to experiment first, make sure that the outcomes are good. But as long as you have the players that bring in the trust, like NVIDIA, like ourselves, like all the hyperscalers, as long as the outcomes are there, we see an adoption. We're adopting it in our life. We use ChatGPT, the Claude, for everything. And we can see that that's coming also into the applications in our world. So I think it will have an impact. It will be adopted. It's just that we, the providers of technology, just need to make sure that we do it right. We do it within guardrails so that the trust is not broken, and then the adoption will go fast. There is a retrofit component, however, that we cannot ignore. Facilities have been there for some of them decades. So there is a retrofit element of where do you spend the money to bring in AI to its fullest, and where you do a little bit, maybe less. So tomorrow, autonomy will not be everywhere, but will be in a good place.
Fantastic. Thank you.
And as I said, the main thing is for this models. We talk all about LLMs and the models, and the whole thing is about, when it comes to our industry, is about safe or rigor versus speed. So rigor and speed. So we've been very rigorous, physics-based models. We cannot go wrong, but speed is important in operation, as I was saying. So how do you balance between rigor and speed? How do you balance between a statistical model and a physics-based model? So this is where the balance will happen, and this is where we partner with people like you, companies like you, with Geminus. So maybe I pass on to you now to tell us, how do you do that? How do you balance the rigor versus the speed? And how is it the adoption and the cases that you see in the field?
All right, great. Yeah, so first of all, I'll just maybe give everyone a little bit of background on Geminus. So on the one side, you've got the company with 100,000 people. On the other side, you have the company with 30 people. We are based out of Silicon Valley, a Series A startup, and our roots come from deep academic backgrounds. Our co-founder and our chief AI scientist are MIT, Stanford, and they currently sit in the Michigan Institute for Computational Discovery and Engineering, heading up that institute, which is really the intersection of research and industry in what is possible in the merging together of computation, simulation, and over the last couple of decades, the emerging field of artificial intelligence. So this is the background of our company, and really then what what our mission is to bring AI, and I'm just going to use a general world AI here, to mission critical assets. So these assets where trust and confidence in the answers that we give need to be close to 100%, right? We can't accept 80, 90%, 95%. We have to get all the way up to 100%. And so this is what Geminus is all about, is building out a solution that allows industrial companies to use machine learning and AI to make decisions and optimize their assets in real time. So that kind of gets into this the speed versus rigor.
So Chad, what's a mission critical asset?
Okay, mission critical asset. Yeah. So I think when we think about a mission critical asset, there are two components. I touched on one of them. So the first is about confidence and trustworthiness, right? Again, if I need to run an asset and make a prediction about how to run that asset next, and when I say an asset, I'm talking about a big industrial piece of machinery. It can be a piece of process equipment in a refinery, ammonia. It can be a space and defense application where you can't afford to have approximate answers. So the confidence needs to be very, very high, right? Because the cost of misdesign at the planning stage can be hundreds of millions, or the cost of operational running off of peak operations can be tens of millions of dollars of OpEx every day. So that's one definition of critical. And then the other is around process safety as well, right? You cannot afford, in some instances, you can't afford to take risks and how you run these assets and how you predict to run them next, because people might get hurt or injured or worse. There was just in the news yesterday a situation in Qatar where they were restarting an LNG facility, and unfortunately a bunch of people lost their lives because of the decisions they made while they were restarting that equipment. Unfortunately wasn't optimal. So I'd say that trustworthy confidence, that's one definition or one part of mission critical. And then the other interesting thing about mission critical is the uniqueness of these assets. And when I say unique, there are lots of satellites in the sky that all seem, from our view, they all look the same. There are lots of, if anyone knows about refining, there are lots of fluid catalytic crackers in different refineries. And they all look the same, but the reality is they're not the same. There are differences and nuances in how they were built, and differences and nuances in how they were and how they've been operated and maintained over their life cycle that make them very, very unique. And because of that, again, that you can't treat them all the same. So they're quite different there.
So why do you treat them differently for AI? Can you expand on that?
Yeah, and so I think and this is a little bit about approach, right? This is this idea of you can't use the same type of AI to solve all problems. Everyone in this room, I'm sure, is familiar with large language models, of course, right? Everyone is using them. Our kids are using them. We maybe resisted at first, but now we've adopted because they're an incredible efficiency gain. But back to this idea of trust, confidence, uniqueness, these are massive models that have been trained on massive data sets. And because of that reason, they scale very nicely. But of course, we know we can't trust, right? We know we have to take the outputs that come with those with a pinch of salt because of the way that they were trained, because of the way that they are fundamentally, the math behind them, the algorithmic method behind them leads to a statistical process. That statistical process does not give us absolute results that we need for mission critical assets. In the middle on this image here, you can see is something that maybe you've heard of, but maybe you haven't heard yet. And these are what are called world models. So this is going to be the next evolution that people are going to be talking about 6-12 months from now. And these are also models that are trained on massive sets of data. But unlike large language models, these models understand physics, they understand causality, They have temporal persistence. They understand the flow of time, right? Your large language model doesn't know anything about time. They're able to simulate what-if scenarios. They're able to give you prognostication over what might happen next in a physical system. And so this is like a large language model in that it's trained on very large amounts of data, but it does understand physics, and it has all these other kind of benefits. So we'll be able to tackle engineering problems. You have one here in France that is being launched by Yann LeCun. Jeff Bezos is promoting Prometheus, Google DeepMind, Genie A3. So you know, there are big players and billions of dollars trying to tackle this front. On the other side, we have a slightly different view of the world at Geminus, and we love LLMs. We use LLMs. They are foundational for how we solve problems. We are going to embrace world models also, but we have a view that at the industrial level, in your industrial assets, you need to take a more neighborhood approach. And that is because the way that your plants work, the way that your industrial systems work, there is no data set that is available from far that you can train in order to understand the way that system works. You need to come all the way down to the local level. I think we lost the mic. Are you on still? Hello? That one's still on. You need to come all the way down to the neighborhood level in order to really understand an asset and then be able to predict how it works.
Maybe you can see that there is very similar concept here between us, that it is really in our industries you have to go into either foundation models, which are domain specific, like time series for ESPs, electrosubmersible pumps, like a drilling time series time model, or even take it further where you go to a neighborhood model. So can you maybe just make it more concrete for us? What is it?
Sure. So this will be interesting if we can use a metaphor in two languages, but we'll see if it works. So the idea of a neighborhood model, so again, unlike treating the entire world in big data sets, so if you come all the way down into a neighborhood, so here is a neighborhood of houses, right? And imagine inside the houses, people, there are cars that are coming and going from the houses, there are roundabouts that can only handle so much traffic, and then those roads lead into a parking lot. And inside that parking lot, the people that get out of their cars, however many cars come, can maybe go to Carrefour, they can go to Fnac. Understanding the dynamics of that system and how people are going to move each and every day, and whether they're going to leave their house at 9 a.m. or 12, whether it's one person coming out of the house or two people, whether once they get to the parking lot, or maybe there's a traffic jam in the roundabout that way, and once they get to the parking lot, do they have to go buy eggs or do they want to go buy a computer? There is no large data set that exists that can predict how that system works. You need to go all the way into that system, and it's not even a model. There's not even a historical data set that tells you how that system is going to work. You need to combine historical data together with sensor data. You need to be able to measure things in real time that give you some predictive element about how the system is going to behave. You still need to obey the laws of physics, causality, time, temporal, you need all of that like world models have, but you need to get all the way down into that system in order to really understand and predict how people are going to flow and where they're going to go. That's a metaphor for an industrial system, right? You can pick any industrial system you want where you have inputs and outputs. You have machinery that is transforming these inputs into outputs. Sometimes those machines, they drift, they change over time. There is no big data set that describes how, imagine a process that has a catalyst. That catalyst changes over time. That it wears, it oxidizes, whatever. You can't describe that system from far, so you can't have 99% confidence. You need to go all the way down into the neighborhood to describe that system.
Sure, there are challenges with these models as well, right? The more you go down to the specificities, there has to be some challenges, maybe also touch a little bit not only on the challenges, but also the scale. Because if you go down to a specificity, how do you go back up and scale that to other cities in your analogy, for example?
Yeah, exactly. So I will talk a little bit then about the challenges of this neighborhood model. So the beautiful thing again about large language models and eventually world models is that big data sets, you manufacture big data, you train on big data, you get a result. When you get down into the neighborhood, the question is, where does the data come from? And so the first challenge you have to overcome, and I'll talk about how we overcome it, is what we call data gap, right? So how you cannot make AI, you cannot make machine learning models if you do not have the right data. So you need to find the right data, and you need to, if anyone who's implementing any type of AI, that's like one of the first questions that you should really try to understand is how am I going to get the right data in order to make a high quality, high confidence model that understands the uniqueness of my system, okay? So that's number one. The second thing is what we call pervasive uncertainty. And so what we mean here is that even things that even numbers that you take for granted and values that you think are absolute and certain, the reality is they're not, right? When you turn a valve and you think you've opened it 4 centimeters, is it actually open 4 centimeters, or is it a little bit more or a little bit less? You can take that concept and extend it over a bunch of different physical parameters. And so understanding uncertainty and being able to make decisions in spite of that uncertainty is also another massive problem that needs to be solved. And then the third is understanding that every node in a system, if you think of those little orange and white dots as pieces of machinery in a system, every node in a system is also dependent on every other node, right? The inputs from one process, the outputs from one process are inputs to another process, and so what changes over here impacts what happens over there. And so, again, when you are training artificial intelligence over a system, you can focus on a single node, but then you're just going to reach the constraint, the maximum of the next node in the system. So you need to be able to understand the system as a whole. So these are the challenges. So then what do you have to do to be able to solve this? So again, just as a way, this is the way we think about these problems. If people don't know how to take many different sources of information, all different sources of information, and fuse them together into one complete model, what we call the data quilt, then we think ultimately the solution's not going to be robust. So what are the different types of information? So here we're talking about physics-based simulation, right? So when you're solving engineering problems, most companies have a rich history, like SLB spoke about, like Amanda spoke about, is they have a rich history in using physics-based simulators to design and plan. Those are great sources of information that are bounded in physics. Historical data, obviously, real-time data, that also helps understand the state and status of systems. But now also with agentic systems, we can build physics-based solvers. We can build physics-based mathematical representations of systems on the fly. And so that's another source of information, and the ability to take all of those disparate things and merge them together into one comprehensive model is absolutely necessary to describe that neighborhood in great detail. The next in any agentic system and dealing with uncertainty is about guardrail decisions. So Amanda talked a little bit about how the domain knowledge comes into play when you're trying to give your agentic system an understanding of how to make decisions. Because of course, a lot of agentic is by nature stochastic. It is, the way it makes decisions is probabilistic. So you have to give it the right guardrails so it makes good decisions. This is down to choices of computational algorithms. It is down to different methodologies that can be used. So in Geminus, we actually don't have data scientists. We have computational physicists. And they, over time, and most PhD labs across the world have learned how to solve these problems. But of course, they can't do it at scale, and I'll talk about scale in a second. But anyway, so this is the idea of guardrail decisions. You have to make the right decisions on how to solve the problems. And then finally, of course, because you are one node amongst other nodes, you have to be accurate at the node level, but you also need to be very aware of everything else that's happening around you. So the ability to construct a system and deconstruct a system and then couple it back together, this is what we call systems of surrogates and systems of ML models, is also critical in order to make this thing work at scale. If you can't do all this at scale, then you're in pilot land, you're in proof of value, you spend your entire time training and never deploying. You need to be able to tackle all of these problems sort of simultaneously, otherwise you can't do this at scale.
Thanks, Chad. I think we're almost out of time. So maybe just to close this, clearly we can see that there is a move from LLM world, and we have a lot of models and we all use them, but really in our industry is how do you make that concrete for the complexities of the industry, be it foundation models or neighborhood models. Just to close, because we're on time, maybe just, is this real today? And then I imagine that the audience has understood that this can be extrapolated. It's not an energy-only sector or oil and gas. It's the similar concept everywhere.
Yeah, so this is real. So we have now, we have taken this in partnership with SLB. We have deployed this to a number of different customers across the world. And so, in fact, we are in the middle of refineries in closed loop control of very complex, non-linear assets. We've taken control of the surface production network in Bahrain. Well, before it was shut in, because of course they had to shut in given the recent events. But you know, controlling the production coming from wells and how it flows through the pipeline networks and how they control the routing decisions, right, of where the gas goes, and giving them the predictive tools to say, you know, given what the dynamic nature of what's happening at a well level or maybe at a compressor level that's downstream, you know, how do they open this valve or close this valve or choke this well or open this well, right? And so yeah, this is absolutely alive in the real world. And then outside of oil and gas, we are I would say less commercial, but we have pilots in defense around image compression, inference, and we also have another one around microgrid. So taking a remote deployment of batteries, power, and then optimizing that system in a remote location for a defense. I can't name the country, but you know, so yeah, the same concept actually works across all physics and across all industries. Yeah. So we open for questions, maybe. Great. Okay. I think we don't have a lot of time, but if there are any questions, we're happy to take whatever you have, or a coffee. Yeah, you can always find us. Yeah. Brilliant. Thank you very much for your attention.